if you remember back to what we talked about last time, we talked about matrix exponentials and the fundamental matrix. So these are tied together. And then we sort of got into a sidetrack. We said, you know, there's this notion that the fundamental matrix is doing what we want that e to the at to do. And then we're like, well, we could compute e to the at if we think about thinking of it in terms of the Taylor series for the exponential function, just plugging in at and carrying out that computation. So we're going to start with an example. So without computing any eigenvalues or eigenvectors, compute e to the at for this 3 by 3 matrix. And finish it before class ends. All right, well, where do we start? Well, the good news is we have a formula. So we start chipping away. What are some things we're going to need? Well, we need the identity matrix. Okay, we have that one. We need A. Okay, we have that one. What else will we need? A squared. All right. Well, should we actually carry it out, or do you trust me? And I can tell you what the answer is. Trust? Wow, you trust me. That's awesome. Thank you. All right. So if you compute a squared, you get minus 6, plus 6, 0, 0, 0, minus 6, and plus 6. Okay. So that's a squared. What else will we need? A cubed. Okay, so now we can work that out, or you can trust me. Do you have a preference? Wow, you guys are great. I like that. Now, a cubed is 0, 0, 0, 0, 0, 0, 0, 0, 17. No, just kidding. It's 0. It's all zeros. It's all zeros. Okay, what else will we need? A to the 4th. Okay, now I'm not going to work that one out, but what can you tell me about a to the 4th? Yeah, it's also going to be all zeros. In fact, what's going to happen for the rest of the powers of a? They're all 0. So we say, oh, this is good. Because what it means is we don't have a lot of ... In fact, all that stuff from the a cubed term on disappears. So that for our particular matrix, we have that e to the at is equal to I plus t times a plus 1 over 2, because that's 2 factorial is the same as 2, t squared a squared. Everything else drops out. So we say, all right, we know what these matrices are. So the identity matrix, we know. That just means you have ones on the diagonal, zeros off the diagonal. We have A, because it's right there. So we just write down 1, 2, minus 1, minus 6, plus 6, and minus 5, minus 4, 5. And 1/2 t squared, and we write down what the a squared is, minus 6, 6, 0, 0, 0, minus 6, 6. So let's put this all together. Okay, so one matrix to rule them all. What's in the first entry? So in the first entry we'll have 1 plus t. Yeah, 1 plus t minus 3t squared. Okay, moving along that row, what's the next entry going to look like? Well, we'll get 0, then we'll get 2t, and minus 3t squared. The last entry, what will that look like? Minus t and 3t squared. Okay, one row down. Okay, next row, middle row, first entry, we have minus 6t and that's it. Next entry. We have a 1 here and a minus 6t. So 1 minus 6t. And there's another term from there. The last entry here in this row, 6t. Okay, bottom row, first entry, what do we have? Minus 5t and minus 3t squared. Middle entry, minus 4t, minus 3t squared, and the last entry, one plus 5t plus 3t squared. All right, good. That didn't take all of class. Well, that's all right. We have other stuff to talk about. But I want to point out, we've actually done something kind of remarkable. Okay, so let's talk about what we have here. Now, this is e to the at, because it says it right there, e to the at equals that. But in terms of what we've been talking about, what's another way to think about e to the at? Something fundamental to our discussions. What? Or something over here. Something fundamental to our discussions. A matrix of sorts. It's a fundamental matrix. So this is a fundamental matrix. So whenever you compute e to the at, you are really doing a computation of a fundamental matrix. Now, fundamental matrix says there should be a differential equation problem. We haven't written one yet. What's the differential equation problem that corresponds to this fundamental matrix? X prime equals ax. Yes. So what we have is, if we sort of think about our differential equation, we have x prime 1, 2, minus 1, minus 6, minus 6, 6, minus 5, minus 4, 5, x. That differential equation has this as a fundamental matrix. But what makes up a fundamental matrix? What are the columns? Well, they're not just eigenvectors, they're something else. In terms of the differential equation, how do the columns of the fundamental matrix relate to the differential equation? These are solutions. We just produced the full solution to this differential equation. So, in general, a solution will look like some constant, I'll use a little a, times the first column plus some constant little b times our second column, and you can probably guess where we're going, plus some constant little c times our last column. So this right here is the set of all solutions to our differential equation, x prime equals ax. So this is kind of cool. It says, hey, we can solve this differential equation problem if we can compute e to the at. Now, generally speaking, it's usually easier to solve our differential equation problem and use that to find e to the at. But this says there's exceptions. There are some cases where it's actually easier to run through this computation because it becomes a very simple computation. Now, some of you, hopefully all of you, got to do the homework and remember, like, 3x3 systems, repeated roots, it didn't seem this easy. But that's because we didn't have the tools. It turns out it can be this easy. Well, almost. There's something special about this particular matrix. Anybody have a guess as to what the eigenvalues of this particular matrix are? So the eigenvalues of this matrix are 0, 0, 0. So all the eigenvalues being 0, that's essentially what causes it so that eventually you get the 0 matrix if you raise it to a high enough power. So we have the following idea. We say a matrix is nilpotent, don't worry about the terminology. Basically, nil says it's going to 0. If a to the k equals 0 for some power k, so eventually it becomes 0 is what you should think of it. Well, that just means all the eigenvalues are 0, and we've already said, hey, for these matrices, e to the at is nice. You only have a couple of pieces. Now, that's nice if all the eigenvalues are 0. What if all the eigenvalues aren't 0? What if they're all some other number? Well, it turns out that for any value lambda, e to the power at, so a is a matrix, lambda is an arbitrary number, is e to the lambda t, e to the a minus lambda it. And now the magic. It turns out, and I keep saying it turns out, the punchline. If I have all my eigenvalues are the same, and I take a minus whatever that eigenvalue is times I, that matrix A minus lambda I has all the eigenvalues 0, which means it's easy to compute. So, the punchline. If you have a 2x2 matrix and the eigenvalues are both lambda, then e to the at, well, you pull out the e to the lambda t, you have the identity, you have your first term, and then the rest of the terms are 0. So that e to the at is very short to compute. So let's try an example. Here's a matrix, A equals 2, 1, minus 4, 6, and we're asked to find e to the power at. All right. Well, what's the first thing we should do? Find the eigenvalues. All right, so we start our process. 2 minus lambda, 1, minus 4, 6 minus lambda. Take that 2x2 determinant. So we have 2 minus lambda times 6 minus lambda. Subtract negative 4 times 1. So that's 12 minus 2 lambda minus 6 lambda plus lambda squared and plus a 4. Or lambda squared minus 8 lambda plus 16. Does that factor nicely? How does it factor nicely then? Yeah, this is lambda minus 4 squared. All right, so what are our eigenvalues? 4 and 4. Like, wow, the same eigenvalue twice. What are the odds? Well, pretty high considering we just talked about that. On the exam, you never know. You're like, well, I don't know what this one is going to do. But of course, in class, we just follow the flow. Okay, so we say, hey, perfect. We're not even going to compute any eigenvectors. Not needed. We're just going to follow our formula here. It says e to the at is e to the lambda t I plus a minus lambda I t. And we just plug in what pieces are. What is lambda? 4, because lambda is just the shorthand for what the eigenvalue is. The identity matrix is the identity matrix 1, 0, 0, 1. All right, what is A minus lambda I going to be? Negative 2, 1, negative 4, 2, times t, and there we go. Let's go ahead and put it together. We can say this is e to the 4t, and then we'll have a matrix 1 minus 2t, t, minus 4t, and 1 plus 2t. And we're done. Now, in terms of the differential equation, just so we can make sure we understand what we've just done, 2, 1, minus 4, 6, so x prime equals 2, 1, minus 4, 6, x. What are our solutions? So our solutions are our columns, and don't forget to add the e to the 4t. So e to the 4t, 1 minus 2t minus 4t, e to the 4t, t 1 plus 2t. So this is actually, once you know your eigenvalues repeat, it's like, zoop, and you get your solutions. I think this is cool. It seems so much simpler. And there's not really a catch. You just have to make sure you know the process. Now, if you're going to mess up, where are some places where people may mess up? Not that you would do it, because you're all good students. I would say that oftentimes it's this piece right here, the a minus lambda I. So make sure that's what you have there. So, all right. Any questions about this? No? Maybe? I think there's a question.
So since it's a repeated eigenvalue, you have to add a t in front like you were in the general solutions of last year?
Well, so when you think about the t is the bumping. This is the bumping. So it's built into the formula. Isn't that nice? It hands it to you what you need. Like, wow. Nice. I think so. All right. So, another example. Use matrix exponentials to solve for x of t and y of t satisfying the following system. X prime equals 5x plus 9y. Y prime equals minus x minus y. Where x of 0 equals 5 and y of 0 equals 7. Okay, so starting at this, what's one of the first things you'd want to do on this problem? So someone mentioned eigenvalues. Before we can do eigenvalues, what should we have? A matrix. It's not really a matrix yet, so let's just go ahead and make that a matrix. So x prime, we grab our coefficients, 5, 9, minus 1, x. Okay, and now eigenvalues. Are you willing to trust us for the eigenvalue computation? We've done a lot of these. Okay, so what are the eigenvalues? 2 and 2. Okay, whoa, repeated eigenvalues. What are the odds? Well, pretty high given what we've been talking about. Okay, now, what should we do next? The formula for what?
So I plus
Well, what should we compute? And how do we know that we're supposed to compute it?
E to the at.
We're supposed to compute e to the at. And how do we know we're supposed to compute e to the at? Because it tells us. Problems are like that. They tell you what to do. Pro tip, read the problem. All right. Okay, so we're going to compute e to the at. And we say, hey, because we have repeated eigenvalues, that's actually pretty simple. first off, we see our lambda is 2. So that's e to the lambda t. So I'll go ahead and put 2t. That's a terrible looking 2, but 2. Wow, I feel like I'm like learning cursive again. Okay, times our identity, 1, 0, 0, 1, plus t, and this is the part which, I've already said, be careful. So now you know, like, okay, I'm going to be careful. I'm going to be extra careful. What's the matrix? 3, 9, minus 1, minus 3. So for reference, just so we make sure we're seeing where everything comes from, we have e to the lambda t, identity, plus t, a minus lambda I. All right, so let's just clean that up a little bit. So e to the at, we have our e to the 2t. And then we have our matrix 1 plus 3t, 9t, minus t, 1 minus 3t. Okay, so that's e to the at. So that's good. We've made progress. But now we're supposed to use it. So how do we use it to help us solve? What's the next thing we do? Someone said we should find this general solution, but we can skip that step. We don't have to find the general solution. We don't have to find constants a and b. Because e to the at isn't just any fundamental matrix. It's the good one. It's the best one. The kind you want to bring home to your parents for Thanksgiving. Mom, Dad, I made a really good fundamental matrix. Because remember, the way that this is formed is it's phi of t, phi of 0 inverse. That's when we say it's the best one. Because why? Well, if you have initial conditions, that says the solution for initial conditions is you just multiply by x of 0. Because that's the answer. This is, we said this was our general solution, so we say, oh, we already have e to the at. Do we have our vector with our initial conditions? Well, we didn't write it down, but what is it? 5, 7. So we're going to take e to the at times the vector 5, 7. This is our answer for the system. So that we have our e to the 2t in front, 1 plus 3t, 9t minus t, 1 minus 3t, times 5, 7. Well, all right. So we have 5 plus 15t plus 63t, which is a big number, but that's okay. It's 5 plus 78t. Yes? 5 plus 15t, 63t. Next line, minus 5t, 7 minus 21t. So we'll have a 7. And we have a minus 5 minus 21, which gives us negative 26. This is the answer to our differential equation system. Are we done? And why not? We have to split it up. We introduced the matrix, so we have to unintroduce it. We have to unravel it. So our final answer, x equals e to the 2t, 5 plus 78t. Y equals e to the 2t, 7 minus 26t. Done. And yes, this was the right answer for x. Woohoo! All right. So you see, when you do have that repeated eigenvalues, that e to the at is really slick because it helps you find the answer, which I would say pretty efficiently. I think more efficient than what we were doing before. All right, good. Any other questions on this one? Then we're ready to switch gears and bring up our last major topic before the next exam. Non-homogeneous ODE systems. In other words, we're adding something there. We've been talking about x prime equals ax. Now we're going to go to x prime equals ax plus something. You say, well, how do we handle this? And we think about, well, we've dealt with non-homogeneous problems before. We know a little bit of how to handle this. Before we had two big approaches. We said, well, there's the method of undetermined coefficients. We know how that works. And then there's the method of variation of parameters. So we're going to basically talk about these two ideas and how they apply in our study. That's where we're going. So let's start with the method of undetermined coefficients. And the idea is essentially the same as what we had before. We say, well, there are certain types of functions that show up. So things like t to a power times an exponential, or t to a power times an exponential times a sine, or t to a power times an exponential times a cosine. These are the same types of things that we were talking about before as the functions. But now, what we have is that our f of t is linear combinations of these pieces, where these things on the end, these are vectors. So, in other words, our f of t can be pulled apart, where each part looks like a nice function, the kind of function we're used to dealing with, times a vector. We say, okay, well, let's just do what we did before. Now, do you remember what the process was? It helps because it tells us you right here. The first thing we said is like, well, let's identify what kind of functions we need to account for. So you say, all right, make sure if you have powers all the way down. So if you have a power of t times anything, powers all the way down. If I have a sine or a cosine, make sure it comes with its pair, because sines and cosines always come in pairs. And then there's one difference, which is the bump. Now, previously when we bumped everything up. And we said, oh, we don't need to worry about the lowest terms. Now, you still bump up, but you keep the low terms. And it's even possible that you might not even use the bump, but a priori, from the start, you don't know that. So other than you don't, when you bump, that you keep the lower terms, the list of functions are the same. And now you say, okay, I have my pieces, and I put them together, but not with unknown coefficients. It's now with unknown vectors. So lo and behold, the big change is the method of undetermined coefficients becomes the method of undetermined vectors. You say, all right, that's what our answer has to look like. We feed that into the differential equation. And when we do that, we're going to get a big system of equations, the same thing as we had before, and we solve for the vectors. And then life is good. So that's the idea. No big surprises. So let's start with some examples. Any questions before we get too far? I think the examples will help. All right. So, give the form for xp. So we don't have to solve for xp. We just have to say, what's the form? Okay. Well, what do we do? Looks a little bit intimidating. But the first thing you need to do is to say, look, let's pull this apart. So when we say this, our function f of t, we're going to pull it apart. And when we pull it apart, we're just saying we're grouping it by the functions involved. So what are some of the functions that we see showing up upstairs and downstairs? Now, they don't have to show up in both. They might just show up on upstairs. They might show up on downstairs. They might show up in both places. Okay, so we see a t, right? I say, okay, so there's a t. What does that mean? What's the part of the vector that corresponds with just the t pieces? 3 minus 2. Okay, so that says we'll just keep track. We've accounted for the 3t and the minus 2t. What else do we have? We have what? Do we have an e to the 5t? Now e to the 5t shows up, but it's not just only e to the 5t. Okay, so we have like t e to the 5t. Okay, so t e to the 5t. What does that look like? What's the vector there? Well, someone said t over 7, but the thing is, I need this vector to be constants. So I'm pulling it apart as function times numbers. So is there anything with the t e to the 5t upstairs? So what goes there? And then 7. All right. What's another function we haven't accounted for? T squared e to the 5t. What's that vector going to be? 1, 0. Okay, what's something else? Sine t. What's that vector? 1, 0. Okay, anything else we haven't accounted for? The 5. So how do we handle that? Well, I like to think of it as the function 1 times 0, 5. That's what I'd recommend. Okay, so have we accounted for all the pieces for f? Everything has a check mark, so that's a pretty good sign. So that says really, when we pull f of t apart, we have our pieces here. So we have the function t e to the 5t, t squared e to the 5t, sine t, and 1. So those are our functions. Good. Is there anything else we need to look for? Someone mentions cosine. Okay, so we should start writing down some other things that we have to add in. So let's make a list, need to add. We need to add cosine of t. Anything else that we need to add? You have to have e to the 5t with no t attached. Anything else? Okay, so we've identified the functions that are showing up. So these are the functions times our unknown vectors, undetermined vectors. We saw that there were some functions that we need to add. Is there anything else before we write down our answer that we need to do? Well, we don't need to do a t squared because we only need to do anything with a lower power. So we have t. 1 is a lower power compared to t, but we don't have like a t cubed. If we had a t cubed, we need a t squared. So we're okay with this. But is there anything else that we need to sort of take some time to look at? Anything at all? Anything that might influence the answer? No. I'm pretty sure that there must be like something that we need to look at. Something we need to just double check. Yeah. Oh yeah, we should look at this matrix. Because we have to know, is there going to be a bump? Now the way we look at the bump is we say, well, what kind of functions are showing up in this matrix? So the key thing is the eigenvalues. Wow, what a surprise. An eigenvalue computation? Yeah. Just think when you take linear algebra, you're going to be like, I'm so good at this stuff. I'm a pro. Okay, so we run this computation. 4 minus lambda minus 1 minus lambda subtract 6. So that'll give us lambda squared. And then minus 4 lambda plus lambda is minus 3 lambda. And then we have minus 4 minus 6 is minus 10. That factors. Lambda minus 5, lambda plus 2. So what are our eigenvalues? 5 and negative 2. Which means that our solutions for just the x prime equals ax looks like x equals some constant c1 e to the 5t times some vector, we don't know, plus c2 e to the minus 2t times, again, some vector we don't know. But we care about the pieces in the front, so the e to the 5t and the e to the minus 2t. Is there any overlap? Yes, there is. So there's overlap, so we need to say, okay, I have to account for the overlap. So that says I need to be bumping up the e to the 5t's. So what do I need to add to my list? T cubed. Why? Well, because we already have e to the 5t, we already have t e to the 5t, we already have t squared e to the 5t, so we need to add the next one up, which is t cubed e to the 5t. We keep e to the 5t. That stays there. All right. Now that we know our pieces, the general form is pretty quick. So we'll have x equals 1 times some vector plus t times some vector plus sine of t times some vector plus cosine t times some vector plus, I'm just putting these roughly in order, e to the 5t times some vector, t e to the 5t times some vector, t squared e to the 5t times some vector, t cubed e to the 5t times some vector. Now, we're not done yet. We've got to fill in the vectors. What's going to be going into these vectors? These are going to be unknowns. So we're going to do our alphabet. All of these are constants. A, B, C, D, E, F, G, H. Should we do I? Yeah, let's keep it. I, J, K, L, M, N, fancy O, P. So now we just have to determine A through P. And then we're done. No, we don't, because that's not part of our particular solution. We're after our particular solution. So we don't need to worry about that. The only reason we computed this was to make sure, do we need to do any bumping? So for e to the minus 2t, no bumping was needed. All right. So we have a few minutes. Let's actually work a problem. Find the general form for solutions to x prime equals 3 minus 1, 1, 1x, plus 3e to the t, 2e to the t. So notice here we kept it a simpler function. So this is e to the t times 3, 2. All right. Do we... Well, okay, so we should do a quick check. What are the eigenvalues? So eigenvalues will be lambda squared minus 4 lambda plus 4, which is lambda minus 2 squared. Oh, deja vu. Equals 0. So our eigenvalues are 2, 2. Now, that's good for us to know. We'll come back to that. In terms of the particular solution, what does that say about our form for xp? There's no overlap, so xp looks like e to the t times some unknown vector ab. No bumping is needed because our eigenvalues are 2 and 2. So how do we find a and b? Yeah, we plug it in, exactly. So we're going to look at xp prime, set this equal to 3 minus 1, 1, 1 xp, and add 3e to the t, 2e to the t. So when I take the derivative of e to the t times the vector ab, what comes out? E to the t times the vector ab, because the derivative of e to the t is e to the t. That's supposed to equal 3 minus 1, 1, 1 times e to the t times ab plus 3e to the t, 2e to the t. Now, everything has an e to the t attached to it. So what can we do? Divide out and cancel. So we have a times b equals, carry out the multiplication, 3a minus b, a plus b, plus 3, 2. Or, that would say what? A equals 3a minus b plus 3, b equals a plus b plus 2. Can we solve for a or b? What is a? A is negative 2. Okay, so if you come here, this one says b equals 2a plus 3. So what is b? Minus 1. So that says our particular solution is e to the t times minus 2 minus 1. Okay, so that's our particular solution. Do you have another 60 seconds so we can get the general solution?
Yep.
All right, general solution. We know our eigenvalues are 2, 2, so what can we do? We can do e to the at. So that's our e to the 2t, our identity, plus t. Then we take our matrix, subtract 2. So that's 1, minus 1, 1, minus 1. So that's e to the 2t, 1 plus t, minus t, t, 1 minus t. So our answer, the columns of e to the at are the solutions to the homogeneous part. So some constant, capital C, e to the 2t, 1 plus t, t. Some constant d, e to the 2t, minus t, 1 minus t. So this is our xc. And then toss on the xp on the end. E to the t minus 2 minus 1. And that's it. All right, thank you. Have a good day.